Hey everybody, Chris McClure here. This is actually the second time that I've recorded this lecture. The first time I did a little bit ago, the audio did not record, but everything else did. But I wanted to make sure that you got the audio, so I'm re-recording this before I go out to dinner. So I'm a little bit hungry, so I'm going to get through this in an expeditious manner. But I'm not going to cheat you out of the experience of dealing with functions. Now, what is a function anyway? We've all heard this term, but really, what is it? Well, the short answer is that a function is a special relation. Okay, what is a relation? Well, a relation is just an ordering between two sets of numbers, but they don't have to be numbers. Those sets could consist of names of people, or years, or fruit, vegetable, grams of fat, calories, countries, whatever. But the relation is just going to tell you the rule that says for each item in the one set that that element gets assigned to the element or some element in the second set. So for each country in the world, there is a population. For example, for each person, there is a cell phone number. For each baby, there is a weight. For each person, there's an age, etc. All right, so we have already dealt with relations as well. When you see an equation involving two variables, then that really defines a relation between the two variables that says that for all the values of x, for example, in this equation here, that if you want to know what y is, you just tell me what x is. And then you'll, do some number crunching and out pops a value for y. So if x is 1, for example, then take 3 times 1, which is 3, minus 1, and you get 2. So the number 1, the value of x, gets ordered or associated with or assigned to, whatever you want to call it, the value of 2. Input a value for 1 and out comes a 2. Input a 0 for x and out comes a value of negative 1 for y. How come? Well, you plug in the 0 for x. 3 times 0 is 0, minus 1 is negative 1, etc. So this graph right here shows you the relation between x and y. The x being the list of real numbers here on the horizontal, and the y being the set of outputs along this vertical axis. And when we want to specifically discuss this relation between x and y, we can use this notation here, x0, y. Okay? So what we're looking at here is another relation, a relation between states and the number of representatives. So you notice that each state is going to be assigned to a number of representatives that state has to Congress. Those are ordered pairs. Alaska, 7 is one ordered pair. Arizona, 8 is another ordered pair, and we've got all these other ordered pairs. Notice that both Colorado and Alaska are assigned to 7 because they both have 7 representatives. That's okay. We would have a problem, though, if we have a relation where some state has 2 different numbers of representatives. That would be kind of chaotic, huh? We're coming to that. So now we're going to start thinking about, well, is a relation a function? Now, You have the big set of relations out there, but only some relations are functions. Not every relation is a function, but every function is a relation. Take a look at this picture up here. Look at this relation between persons and phone numbers. Now, notice for Dan, for Gizmo, and for Phoebe, they each have one phone number. But notice that Colleen has two phone numbers. So, if you ask me any one of these four people, well, for three of them, I could tell you their phone number. But for Colleen, if you ask me your phone number, I could tell you 555-8294. And if you ask me again 5 minutes later, I could tell you 930-3956. Would I be wrong? Maybe, maybe not. Maybe she's got both numbers. Maybe one is an old number and one is a new number. I don't know. But this relation that you see here is an example of a relation that is not a function, where a phone number is not a function of person. But this relation down here is a function. So, because each animal has one life expectancy, it's not like you're going to have one dog with two different life expectancies. So here's kind of a picture that shows a function, a little bit more esoteric, a little bit more general. This green blob right here shows a set of numbers called the domain. We call the domain maybe capital X. That's this capital X right here. And a little x represents some element, some number in the domain. And each number in the domain will get mapped, assigned to whatever, some value in this other set called Y. And within the set Y, we have the set of images of the domain. Meaning, for all the different values that X could be in the domain, the function F is going to give you some functional values, some values for Y. And that whole set of values for Y is called the range, which may be a subset of the larger set that you're mapping into. So for example, right? Now, I'm not going to write it down, but imagine that you have the function y equals 1 over x. And yes, that really indeed is a function, because for each value for x, there is one and only one value for y. So you can think about the domain here as the set of all numbers except for 0, because you cannot divide by 0. Now imagine y here. This big function, or this big set y here, imagine that's the set of real numbers. The range is going to be the entire set of real numbers except for 0. Because, 1 over x is never going to be 0. Okay? So the green blob is the set of real numbers except for 0 in this case. So that means the number 0 is very well represented by the red, maybe overrepresented. Anyway, so folks, this right here is a function. This relation is indeed a function. For each level of education, there is an unemployment rate. And notice, by the way, that as you go up in educational level, the lower your chances of being unemployed. So good for you that you are a college student and that you're working on your degree, so that you will decrease your chances of being unemployed. The domain is going to be these 4 levels of education. The range is going to be these 4 percentages. Okay? And you could write the domain and the range as sets. Here's the domain, here are the sets using the curly brace notation. And here's those 4 percentages within a set of curly braces. All right, moving along here. Is this relation a function? And look over here on the left for each of these sandwiches. Is each sandwich with their calories mapped to one and only one level of fat, as in grams of fat? And the answer is yes. For each sandwich, I'll tell you what the fat is. You tell me a sandwich, and I'll tell you the fat content is. And let's see here. It looks like the Burger King Whopper has the largest amount of fat. No, I'm sorry, 33. Oh my goodness, look at the Big Mac. Big Mac's got 33. Well, I just had one of those a couple of days ago. I better go get my cholesterol checked. Anyway, but is this relation now I'm thinking calories, but is this a function? The answer is yes, because for each input there's only one output. Even though there's two sandwiches that have the same number of grams of fat, that's okay. This is still a function, as long as for each input there's one output. If you want to talk about what's the domain, well, it's these calories here. It's these these 6 sandwiches calories. So you go ahead and list them. And the range is going to be these 5 numbers, all written in set notation. Now here's an example of a relation that is not a function. In this example here, you have 2 diamonds maybe with the same weight, carats of 0.86, but that sell for 2 different prices. It could be that one is cloudier than the other or has a different cut than the other. So price is not necessarily a function of weight. You could have 2 diamonds that weigh the same but sell for different dollar amounts. And in particular, you have one element in the domain that gets mapped to 2 or more elements in the range. So that's not a function. Look at this function. Is this a function right here? Is this relation a function? It is a relation because you look at the numbers in the domain, the 2, 4, 3, 2, and you look at the range, the 3, the 1, the -2, and the -1, the second coordinates of those ordered pairs that makes up the range. Is this, though, a function? Well, the answer is no, because of the fact that you see the 2 gets assigned to both 3 and to -1. So as long as you have at least one value of x, meaning the first number, that gets assigned to 2 or more values for y, then that relation is not a function. What about this second relation here? Function or no? So again, look through the first coordinates here and see, are there any repeats? And the answer is no. So that means that this relation is a function. How about this relation down here? And the answer is this is not a function because 4 appears twice. 4 gets mapped to 3 and to -3. So this is not a function. Moving along here. How about this equation here? Does this define a function? Is y a function of x? Well, for any value of x, will you get only one value of y? And the answer is yes. You tell me what x is, I'll multiply by -1/2 and subtract 3, and you'll get what y is. So I could always predict what y is, depending on what x is. So that was a function. Now this guy right here does not define y as a function of x. Because if you tell me a value for x, then I could have potentially 2 or more, up to 2 values for y. You could see that by taking this equation and solving for y. And you get y is equal to plus or minus square root of x minus 1. So, for example, if x is equal to 2, 2 minus 1 is 1, and y would be plus or minus 1. So for one input, I would get two outputs. So this equation does not show y as a function of x. Okay? Moving along here. Now let's talk about evaluating functions. Finding the value of a function by using function notation. Suppose that we've got f of x is equal to x squared. That means that if I want to know the value of my function f, by the way, we like to give functions letters as names. F, G, H, K, J, sometimes. Usually F, G, H. Could be other letters of the alphabet, though. And then followed by the open and closing parentheses with either the independent variable x or some number that you want to evaluate your function at. So if you want to know what the value of the function, well, you square it. That's really what this rule says. Tell me a value for x, don't square it. So if x is 1, then f of 1 is equal to 1 squared. So 1 gets mapped to 1 using this function. Also, negative 1 gets mapped to 1 because negative 1 squared is 1. 0 gets mapped to 0 because 0 squared is 0. Well, f of negative 2 is negative 2 squared, which is 2. So negative 2 gets mapped to 2. In kind of the same story for these other functions here, you see this functional definition right here that will tell you how to find the range given the domain. For each number in the domain, I could tell you what the assigned value is in the range just by taking the reciprocal in this case. So the reciprocal of negative 2 is negative 1/2. That's what f of negative 2 is. F of negative 1 is negative 1. F of 4 is 1/4. How about this function down here? You have g of x, the square root of x. You tell me what x is, I'll take the square root of it, and that's going to be the functional value. Square root of 0 is 0, square root of 1 is 1, square root of 2 is square root of 2, square root of 4 is 2. So you see these different functional values. It is common for us to evaluate functions by replacing x by the specific value for x within the parentheses. So g of 2 means the value of g when x is 2. The g of 4 means the value of the function g when x is 4. How about this function here? We have g of x is equal to 3. That means that regardless of what x is, the function's value is always equal to 3. So if x is equal to 0, well, g is 3. If x is negative 2, g is 3. X is 3, g is 3. Though that's a real simple function. Regardless of what x is, g is 3. So whether you have a simple function or a very complicated function, a function is basically a machine where you plug in a value for x and then you figure out what that value of f is for that given value of x's. You might have to do some math, some algebra to figure out what that value of x is, but you're essentially simplifying some expression or maybe looking some number up in a table or something like that, but you got to figure out the value of f, and out pops that value of x. So the y value, the corresponding y value, will be that output of the function. In other words, that functional value. So that's why we have this equation that y is equal to f of x. Now, this notation you have to get used to it. This takes some getting used to. A couple of comments, though, that your function is not always going to take all values of x from the real numbers. Meaning, there are some functions like square root of x where you cannot plug in any old value of x. And like square root of negative 1 doesn't exist. Square root of any negative number doesn't exist, at least in the real numbers. So we'll have to make sure that the numbers that we plug into the function belong to the domain for that expression which defines that function. And also note that there's exactly one output. That's what it means for your relation to be a function. For each input, there's exactly one output. So let's get a little bit of practice evaluating a function. Suppose that we've got the function f of x is equal to negative 3x squared plus 2x. Let's evaluate the function at these 8 different values. First of all, f of 3. Now, f of 3 means that you take a look at your function and see on the right-hand side, we've got this expression, negative 3x squared plus 2x. Well, you evaluate that expression at x equals 3. You plug 3 in for x, like we did here, and simplify. You have negative 3 times 3 squared, that's negative 3 times 9, which is negative 27, plus 6 is negative 21. So f of 3 is equal to negative 21. Okay? Suppose that you need to figure out or evaluate f of x plus f of 3. Well, f of x is negative 3x squared plus 2x. F of 3, we already figured what that is. That's negative 21. So f of x plus f of 3, that's negative 3x squared plus 2x plus negative 21. And there you go. There it is. That's what f of x plus f of 3 is. All right, here's the next one. 3 times f of x. Well, f of x is negative 3x squared plus 2x. So multiply by 3 right here. And there you go. You've got negative 9x squared plus 6x. The next one, we have f of negative x. Well, replace x by negative x. That's what this is telling you to do. Replace x by negative x into the expression and simplify. And you get negative 3x squared minus 2x. Moving on to part E, the negative of f of x. Now look, before I go on, do you think that f of negative x is going to be the same as negative f of x? Well, the short answer is it depends. It depends on the function. For this particular function, if you replace x by negative x, let's see what we get. Here's negative f of x. And that's the negative of negative 3x squared plus 2x. And the result is, of course, you're just switching signs here. You get 3x squared minus 2x. And that's not the same as f of negative x. And if you want to do f of 3x, well, replace x by 3x and simplify. You want to do f of x plus 3, replace x by x plus 3 and simplify. Collect like terms. You want to do f of x plus h minus f of x over h. It looks a little complicated, but again, replace x by x plus h minus f of x over h. By the way, h is a constant, so treat it as such. So now you just multiply all the stuff out. Negative 3 times x plus h squared. Well, x plus h squared is x squared plus 2x plus h squared. Then multiply by the negative 3, combine like terms, simplify. So a couple of algebraic steps. I'll let you check the details. When you go over here, collect like terms, factor out an h. That's what we've got here. Cancel the h's. And then you're left with this expression right here. Negative 6x minus 3h plus 2. Remember, h is a constant. So negative 3h plus 2 is a constant. So you got negative 6x plus some constant. Moving along here. Now, if you want to use your calculator to evaluate functions, no problem. I'm going to pull out my trusty calculator here. And because of the fact that this is my second recording of this program, I already have this stuff loaded up my calculator, so I'll show you real quick. Now, what you need to do is go into your equation editor and load up a function or 2 or 3 or whatever. So put in your function in your equation editor. Now, if you have some equation where you got your x's and y's mixed up, make sure that you take that equation and solve explicitly for x, and then put in that expression involving x into the equation. And notice that my functions here are a little bit out of sync with what is shown on the slide, but that's okay. The point is that we want to know, how do we evaluate functions? Though there's a couple ways that I could show you. Suppose that you wanted to figure out what is y equals x squared at some value of x. Now, this is a real easy function. I could, even on the home screen, just put in that value for x and then use this button here to square it. But suppose it's some other weird value, some function like x to the x power or something. Anyway, so I'm going to just show you how to do this. So let's quit out of the equation editor. So you know what y sub 1 function is, y sub 2, y sub 3, what all those functions in your equation editor. You've got those functions loaded in, and you want to evaluate those functions at different values for x. Now, did you see this variables button here? Click on variables. And in this window here, you have the variables, and then you have the y variables. Right arrow over to the y variables menu, and then select this first option, option 1, where it says function. And then select the y sub whatever function for the function that you want to play with. Let's suppose that we want to take the square of some number. And remember that y sub 1 is x squared. So we'll choose y sub 1. Otherwise, we could scroll down and scroll up to choose our y sub 1, our function, whatever. So let's choose y sub 1. And then to evaluate y sub 1 for some value of x, we'll do an open in parentheses and plug in a value for x, like 1.234. And close parentheses. So before I hit enter, let me just explain what we're doing here. We are going to evaluate the function y sub 1 equals x squared for x equals 1.23. And now hit enter. For example, suppose that I want to take the square root of some number, then I'll choose variable y sub 2. So let's repeat what we just did. So we'll just choose y sub 2, open parenthesis, plug in a value for x like 1.234, close parenthesis, enter. Or maybe we want to take the reciprocal of some number, that's y sub 3. So variables, y variables, y sub 3, evaluate at some number like 1.234, close parenthesis, and there. I've evaluated my 3 functions at some value for x. There's a different way, and that's going to be used in the table. This way, I like it a lot. It has its own strengths and weaknesses. So let's first go into the table setup. Click on second and go into the table setup here. And let's start off at a reasonable value for x, as in like 0. Enter. Now, I'm going to actually have you scroll down to independent value variable. And we're going to select ask. So right arrow over to ask, hit enter. And now go over to table. So suppose that I want to evaluate my three functions. You only see two, right? Well, right arrow over all the way over, it'll show you all the functions that you've got loaded into the equation editor. You don't see anything because you haven't specified a value for x. So let's plug in a value for x, like 1.234, and hit enter. Well, the calculator is going to evaluate all three functions at that value for x. Throw in a different value, as in like 67.93 or something. Just dream up some number. And you could see all three functional values by using your left and right arrow buttons. What happens if you plug in 0? Now, if you plug in 0 and the function is undefined there, then the calculator will tell you error. How about throwing in, say, -1? And it's going to have a real problem because you cannot take the square root of a negative number. Yeah. Okay. So anyway, let's go back to table set though, because we're not quite done with this. I want to show you how you can actually have the calculator evaluate your functions for a whole range of values for x along using any sort of increment. Now this delta table, that's your increment. You could have x go from 0 to 1 to 2 to 3 to 4 to 5 and so forth, and have your calculator evaluate your functions at all those different values for x. But if you wanted to do it for every 0.1 or every 0.2 or every 3 or whatever, you could set that increment. Now, just for today's demonstration, we'll just leave delta table at 1. Okay, but down arrow down to independent and select auto now. Enter. Okay, and now go back to table. And now notice that what we've got here. Notice that we have x starting off at 0. If you want to go in the negative direction, you can. Otherwise, go down arrow for the different values for x, and notice that your calculator is evaluating those functions for all those different values for x. If you want to change the increment, just hit the plus button. And this time, I did something there. Interesting. Yeah. Interesting. Anyway, so play around with this. It looks like I was trying to do some bootleg thing with Delta X and it backfired on me. So if you want to do it every 3 units, like 0, 3, 6, 9, and so forth, have it start off at 0 and then go back to table. So there, you could see the different functional values for those multiples of 3, for example. Anyway, we're done with that. Now you know how to evaluate functions on your calculator. So we already did all that stuff. Moving along here. Functions are not always apparent when you see the equation. Sometimes that you've got the x and y terms together on the same side of the equation. Oops. So in order to really see y as a function of x, you might have to do some algebra to move all the other terms over, all the x terms and constants and everything, to the right side of the equation. So you just have y on the left side written explicitly as a function of x. Or you might have to solve for x some other way, in which case you may or may not have a function. But if it's apparent that for every value of x that you plug in from the domain, that you get one value of x, of y, I mean, one value of y and only one value of y, then you have a function. But if you have a square or fourth power or something like that in the equation, that means that you don't have y as a function of x. Here's kind of a quick summary of some facts about functions. I'll just summarize the summary here. This first one basically says that for each element in the domain, it gets mapped to exactly one element in the range. That element in the range is called the image, f of x. All right. Also remember that you could have two values of x get mapped to the same value for y, and that's perfectly fine, as long as for each input there's only one output. Remember that we use f of x to indicate that you have some function f whose value depends on whatever x is. X is the independent variable, and when we say y equals f of x, that means y is a variable whose value is dependent on x. So y is the dependent variable. Okay, let's talk real quick about finding the domain of a function if the function is defined by an equation. And folks, it's really simpler than you think. We've already had this discussion from an earlier chapter when we were just talking about expressions. It's basically the set of allowable inputs, meaning what values of x could you put into that expression so that expression is defined. Like this one right here. We know that for fractions that we can never divide by 0. So one way that we can find the domain is to say it's going to be all real numbers except for the values of x which make the domain, which make the denominator equal to 0. So you set the denominator equal to 0, and you solve for x, and those values of x which make that denominator equal to 0, you will exclude. So in this example here, you will exclude 3 and negative 1, because those two values of x make the denominator equal to 0. So we could say all real numbers except 3 and negative 1 using this notation. This isn't the only notation. You could have the union of some intervals, like from negative infinity to negative 1, plus, meaning union with, the interval from negative 1 to 3, together with the or union with the interval from 3 to infinity. This is a little bit more complicated that way. This way is a little easier, huh? You could just simply exclude negative 1 and 3 and be done with it. The way this reads, though, is x such that x is not equal to 3 and x is not equal to negative 1. All right, let's move on down to this function here. G of x is equal to x squared minus 9. Are there any restrictions on x? And the answer is no. X could be any real number. So the domain for G is the set of all real numbers. What about h here? Well, you cannot take the square root of negative numbers. So only when 3 minus 2x is greater than or equal to 0 will you have a defined function. So you set 3 minus 2x greater than or equal to 0. That means that x is less than or equal to 3/2. You know how to solve inequalities now. So you could write your domain in this set builder notation or with interval notation. That looks like this. All right, moving along here. So finding the domain of a function. So you start with this set of real numbers, exclude any numbers which would make the denominator equal to 0, and exclude any numbers which would make the radicand of a radical that is a square root or a fourth root or any index that is even. So any values of x which would make that radicand negative. Now, if you have cube roots, fifth roots, seventh roots, radicals with odd indices, then that's not an issue. You only have the issue when you have the even indices. So you have to, in those cases, you have to exclude the values of x, which would make the radicand negative. All right, moving along here. In some instances, some values of x just wouldn't make sense in the context of the problem. So, for example, suppose that we have a rectangular garden plot that has a perimeter of 100 feet. Well, look, here's a sketch of our garden plot. It has a certain width w, and it's going to have a certain length l, which we don't see here. But imagine that there's an l right there. And the perimeter is going to be w plus l plus w plus l for a total of 100 feet. 2w plus 2l is 100. That means that l plus w is 50. That means what? That the length is going to be 50 minus w. So the length is 50 minus w times w to give you the area. So there's the expression for your area. What is the domain for this function? Well, it makes sense for the width to be greater than or equal to 0, because after all, you wouldn't really have anything if you have a negative width, huh? But we also cannot have w to be greater than 50, because then you would have an infinitely thin plot. Actually, you would have negative area. So the range of values for w that makes sense in this function is going to be between 0 and 50. Okay, so there's the domain for that function. In the context of the problem, this is the domain that makes sense. So as long as the width of your plot is between 0 and 50 feet, then you will have a rectangle with some area. All right, this next little block involves combining two functions by either adding them, subtracting, multiplying, or dividing them to create a new function. Now, suppose that we got a function f and a function g, and when we take the sum of those two functions, we use this notation. F plus g of x is that function gotten by taking f of x plus g of x. And likewise for f minus g, that's the difference, f times g, and f divided by g. Now, got to be careful and make sure that we're not dividing by 0. So we would have to exclude from the domain of our new function here any values of x which would make the denominator equal to 0. Of course, you knew that. So let's just see how this goes. Suppose that we've got function f, 2x squared plus 3. And we've got function g of x is equal to 4x cubed plus 1. So what would f plus g look like? F plus g of x. That means f of x plus g of x. So you add those two functions together. 2x squared plus 3 plus 4x cubed plus 1. How about f minus g of x? So there you go. You take the f minus g, subtract them. Now, just make sure that when you do the subtraction that you put all of g within parentheses and then distribute the minus sign appropriately in combined like terms. Here's the multiplication of the two functions together. FOIL them out, combine like terms. Here's the quotient, f divided by g. Keep in mind that if g involves a radical or something, you might have to rationalize the denominator or something. Okay. All right, so here's a summary of exactly what we've talked about this block of instruction. We talked about what are functions, basically a special relation between two sets of numbers in which each element in the domain gets mapped as the image to the range. We could have implicit or explicit definitions of functions. Make sure that you're comfortable with functional notation. How do we evaluate functions? Let's talk real quick about unspecified domains. If I throw out some function like square root of 3 minus 2x or whatever, and I don't tell you what the domain is, well, from that algebraic definition of the function, you could tell that not all values of x will make that expression defined. So you'll have to understand that whatever values of x would make you take the square root of a negative number, for those values of x you would have to exclude from the domain. So just because I don't tell you exactly what the domain is, don't assume that it's the set of real numbers. All right, that's really what we're talking about in the unspecified domain here. So there's your functional notation. F is the name of your function. X is the independent variable, sometimes called the argument of the function. Y is the dependent variable because y's value depends on the value of x. F of x is the value of the function. It's the image of x. All right, so that's it for section 3.1, start of chapter 3. So, folks, we're going to continue doing one section a day. I'm here on base all weekend, so I'm just going to record one section each day for the next several days. So just understand that we have a lot of more material to cover. Now, at the start of the semester, I was intending to get through chapter 8. Well, I don't know that we'll get through chapter 8. That seems to be a bit ambitious, but we're certainly going to get a couple more chapters under our belt, going at a pace of about one section per day. I probably won't record anything on 4th of July, and maybe not even on Sunday. Who knows? We'll see. But at least 6 sections per week. All right, remember, for those of you who are getting a little tired and everything, I understand. I feel your pain. I've taken a lot of classes like that too. But remember, this is a 4-credit math class that you are taking over the summer. So hang in there. As we go through the semester, I'm going to be easing up on the homework assignment. So, instead of having 35 questions per section, I'll be trying to ease it down. Of course, it depends on the section, though. If we have a large section with a lot of important material, then we may have to have more questions. But in general, I'll try to be more discriminating in and giving you fewer and fewer problems as the semester. But I want to also make sure, though, that you have the opportunity to interact with the problems. And also understand that not all problems will take the same amount of time. And that there are a number of problems where it takes a few seconds to think about it and then select your answer. I also understand that there are more difficult problems where you have to write the problem down on separate paper and work it out and then input your answers. Also, some people like to, answer the easy problems first and then print out the more computationally intensive problems and log out of my math lab, work out those problems separately on their printed out sheets, and then log back into my math lab later on and input those answers. You have the ability to do that. Also, don't forget, I've posted a quiz for Chapter 2. And after midnight tonight, right now it's Thursday, June 20th. So right after midnight at 0001, 1 minute after midnight, you'll have access to the Chapter 2 quiz. So go ahead and make sure that you're staying on top of the quizzes. Make sure that you know when the quiz due dates are. So log into Blackboard. Log into Blackboard and click on the link for quizzes, and you know click on the quizzes so you know when the due dates are. So just because you click on a quiz doesn't mean that you're going to enter the exam right away. But at least when you click on the quiz, you can see the due date. Also, whenever I post a quiz, I tell you explicitly when the due dates are anyway. So your third quiz is posted, and of course, we're going to get through chapter 3 in a week or so, and yet there will be another quiz. Some people have been asking me about the exam. I talked about the exam in the previous recorded lecture for 2.5, so I'm not going to repeat that discussion now. I'm just going to repeat though that you need to make sure that if you are taking an exam not on the DMAC campus anywhere, but outside of the DMAC area, that you need to send me or have your proctor send me the proctoring form. I've gotten a couple people's recently, but if that applies to you, make sure that I've got your proctoring form. Otherwise, be thinking about which DMAC campus that you're going to take your test at. And so be ready to answer the question, which campus will you test at? All right. So I'm going to wrap this up now and get out of here and go eat some dinner. Take care, folks, and I'll see you tomorrow.